Hi everyone. Today I want to talk about my research on how to enable mixed reality to make it better serve and empower people with low vision who have vision impairments but also have usable vision. To define mixed reality in 1994, Milgram and Cascino present a mixed reality continuum. On one end, it is the physical world where we live in, the reality, and the other end is a pure virtual environment generated by the computer, virtual reality. And in between, there is augmented reality where we can incorporate different virtual elements into the physical world to augment it. And also augmented virtual reality where we can add different physical elements into the virtual world. For example, when you're playing a VR game, you can see your own hands or the controllers. Along this continuum, all the technologies that incorporate both the physical and the virtual elements into one single environment is called mixed reality. And as an HCI researcher, I desire to explore and create technology for social good. And I see the great potential of mixed reality in accessibility by enabling people with diverse abilities. For example, by using AI technology to automatically recognize the environment that people with disabilities cannot perceive. MR can immersively generate different augmentations and feedback that can augment this information and enable people to better perceive and connect to the world. However, on the other hand, mixed reality can also bring a lot of accessibility issues. For example, the current MR is very vision dominant, that is not accessible to people with vision impairments. And also, it can require many different interactions, for example, the hand gesture or the use of controller, which is not accessible to people with motor disabilities. And there is no any accessibility standard or guideline to regulate how to make this technology accessible. So the real world, with all the inaccessible social infrastructure and technology, is already challenging enough for people with disabilities. And now we have MR, this powerful technology that can empower people. Do we want to use it to generate another virtual world that is again inaccessible and further marginalize people? Of course not. And my research goal is to make sure this would not happen. So in my research, I aim to explore how to leverage and also shape the development of MR technology to provide people equal access to both the real and the virtual worlds. And to do that, my research have two core types of contributions. One is a science contribution where I conduct rigorous studies to understand people's behaviors and abilities, and also the innovation contribution, where I design and build novel technologies to address the challenges that people face and promote equity for everyone. And specifically, my research methodology is multidisciplinary. I usually start my research by understanding the people. And take low vision as an example. I conducted both quantitative vision assessments, fully in vision science, and also in-depth qualitative studies via both observations and interviews to understand the user's experiences, behaviors, and needs. And based on that, I also design and build technologies by drawing insights from multidisciplinary fields, including cognitive psychology, visualization, artificial intelligence, and so on. And based on that, I also evaluate my technology with the real users with disabilities via both quantitative and qualitative methods. And besides the scientific contribution, I also desire to make real-world impact. And some technologies I developed are on production level, which were deployed or open source so that a broader audience can benefit from it. And with all of these methodologies, my research branches into three big directions. First, I design and build intelligent MR systems to address the real-world challenges that people face. And besides the real world, I also create technology to address the mainstream MR accessibility issues so that people can also have equal access to the virtual world. And also, since MR largely relies on the AI technology to perceive the environment, I also investigate the use and impact of AI technology, but more in accessibility context, and provide insights to the AI fields. While my research focuses on all these different directions, my talk today will only focus on three research projects, two for the real-world challenges and one for the MR accessibility issues. However, before I dive deep into these three projects, let's first take one step back and look at our target users. So most of my PhD research focuses on people with low vision, which is a large and growing population. So by definition, low vision includes all different visual impairments that fall short of blindness, but cannot be corrected by eyeglasses or contact lenses. And it includes many different conditions. For example, if this is a typical vision that sighted people have, and then if you have low vision, for example, you have cataract, and then your vision can be very blurry, but this blurriness cannot be corrected by eyeglasses. And there can also be many other conditions. For example, people can lose their central vision, can have blind spots, or lose their peripheral vision. And the low vision person can also have multiple conditions at the same time. And all these conditions can bring a lot of difficulties to people's daily life. But the interesting thing is, if you look at these images, you may notice that different from people who are completely blind, low vision people, they still have a lot of functional vision. And the fact is, most of them still extensively use their vision in most of their daily activities. And this can also make the low vision research particularly challenging because it will not only involve technology in the vision, but also a very deep understanding of different visual perceptions. Then how do low vision people use their vision? What challenges do they face, and what technologies can we create to fulfill their needs? So today in my talk, I'm going to answer all these questions via three of my projects. I will start with QC, where I design and build a mixed reality system to address the visual search challenge for people with low vision. I started this research by observing 11 low vision participants in a grocery store shopping task, which is a simple but also very important task for independent life. So during this task, I follow the participants, observe their behaviors, and also ask follow-up questions to understand why they behave and what they can see. So during this study, one key finding is that even though that low vision people face different difficulties across this whole process, but the most challenging and time-consuming task is to find this specific product on this crowded shelf, which is a visual search task. And how they usually do is they have to walk very close to the shelf, pick up each item, bring them very close to their eyes to examine the details, or use the magnifier to see the details and put it back and pick up another one. Scan each item one by one until they find the target, which is a very low efficiency process. So visual search is a very important and fundamental visual task. And many researchers have already tried to put a lot of effort to address the visual search task for the general people with visual impairments. So for example, researchers have designed a system that enable a blind user to take a photo of the grocery store shelf and use the computer vision or human service to recognize a target and then provide audio feedback to guide the user to the target. And some systems can also enable a blind person to scan the barcode on each of the product, and then they can hear the audio description of that product. But they still need to scan each product one by one until they find the target. However, all of these systems, they only focus on people who are completely blind and only provide audio feedback to guide the user to compensate their impaired vision channel. But the problem is, low vision people, they still have a lot of functional vision, and vision is still the most efficient channel that they use during this task. So different from the prior HCI and accessibility research, the key question that I want to address is how can we leverage low vision people's residual vision and provide direct visual augmentations to enhance their visual ability in this visual search task. And inspired by that, I designed QC, which is a new approach for visual search by leveraging people's functional vision. If a user wears a head-mounted display showing the surrounding environment, and then the system can have a camera scanning the surrounding environment and then use computer vision technology to automatically recognize that target for the user. And then the system can render different visual cues to attract and orient the user's attention so that a low vision person can simply follow the visual cues to find the target easily. And now I want to show a demo showing how the system works. So a participant can simply use speech command to speak out the name of the target to assign it to the system.
Look for pea snack.
And then she can scan around the shelf, wait until the cues show up, and follow the cues to get the target.
Look for onion rings.
Okay, so this is how the system works. But to accomplish such a system, the first question, the key challenge is that what visual feedback should we provide, right? What visual cues would be effective enough in this visual search task so that a low vision person can simply follow it in this task? And this question can be particularly challenging because, first of all, many visual cues that are very easy to be seen by a sighted person. For example, this is a very typical visual cue, the blue cursor HoloLens, which is easy for sighted people to see, but is very difficult for a low vision person to notice. And specifically in this visual search task, we not only want the cues to be visible, but also want it to attract people's attention so that they can notice it immediately. And also, on the other hand, we also want the cues to not too distracting to prevent the low vision people to use their original vision to observe the surrounding environment. For example, if a low vision person has peripheral vision loss, then a cue that is relatively bigger that can easily block the user's full field of view and prevent her from using her own vision. So we really need to think about how to balance the visibility and distraction of the cues. And also, at the same time, there are many different low vision conditions that we need to consider. So it's probably we have to provide different design alternatives to fulfill people's different preferences and needs. So to address this question, I first collaborated with the optometrist to understand the different low vision conditions. And I also look into different cognitive psychology theories to understand what visual stimuli can effectively attract people's attention. And by combining all these perspectives, I designed 5 different visual cues to attract and orient low vision people's attention. So a low vision person can select and combine different visual cues they prefer to optimize their visual experience. And I'm only going to give one example. So this one is called Flash, which is inspired by the cognitive psychology theory that onset, which means the appearance of something, can attract people's attention. And to amplify this effect, I add a frame around the target and switch its color between black and gray so that it generates a continuous onset to attract a low vision person's attention. So these are the different cues. But before we put a lot of time and effort into the full implementation, we first want to validate the design of the cues and the system. Then how effective are the cues for people with low vision in a visual search task? To answer this question, I first built a prototype of QC by combining a webcam with Oculus Rift DK2. And I also built a mock-up grocery shelf with 24 different products. But you may notice that there are QR codes on each of the products. And this is because that this study, I only want to focus on the evaluation of the cues so that I ease the process of the computer vision by adding QR codes to remove the confounding effect of the potential recognition errors on the user's experience. So based on this setup, I recruited 12 low vision participants and ask them to conduct multiple trials of visual search tasks in front of the shelf in 2 conditions. One is with QC, their preferred visual cues, and also their best correction as a baseline, which means they can wear their own eyeglasses or use a magnifier if they want to. So in many different research fields, when people do evaluation, they may need a large scale of data or users. However, in accessibility, 12 participants is already a very good number in terms of the difficulty of finding people with disabilities and having them physically to our campus. So based on this study, I want to show two videos to compare the user's experience with and without QC. So this is a participant with low vision, and when he's not using QC with his best correction.
Ready?
Yeah.
Start.
You can see he basically has to get very close to the shelf and scan each of the items. And this process takes very long, so I actually double the speed of the video.
Horizon. Peanut butter. Sound good.
But with QC. So now this video is its original speed.
Ready?
Yes.
Start.
Sound good.
Good.
Man, I wish I had this when I used to work in a grocery store.
So the comparison of these two videos demonstrated the effectiveness of the design of the cues. But the problem is we all know that the study is conducted in a very ideal situation. But in the real store, there won't be any QR codes on any of the products, right? Which means a real product detection component is very important, and its accuracy and speed can largely affect the user's experience. Then how would a real system, a high fidelity intelligence system, will affect the user's experience, especially when the system can have potential limitations such as errors and delays? So to answer this question, I started to implement QC. And I first added a product detection component. So I trained a deep learning model based on a faster RCN model, which is a state-of-the-art object detection model in computer vision. And I trained this model based on RPC dataset, which includes 200 products and 30,000 images. And based on the training, my model can achieve a mean average precision of 0.85, which is a pretty good result in terms of computer vision. However, such a deep learning model would not be fast enough to support a real-time interactive system. So to address that, I also added an object tracking component between each two frames of product detection to speed the system up. And I also added a speech recognition component so that the user can use speech to assign the target to the system. So based on this implementation, I conducted a similar study, but this time there are no QR codes on any of the products, so the system purely relies on the product detection component to do the recognition. And I recruited another 7 participants and still asked them to do different trials of visual search in the 2 conditions, QC and the best correction. And based on the study, I find that QC significantly reduced the participant search time. So this bar charts represent the mean time across all the participants, and the blue bar represents best correction, and the yellow represents QC. And you can tell that the search time was reduced to the 1/3 of the user's original searching time, which is a really big improvement. And in terms of search accuracy, now since we're using a product detection component, so the final search accuracy is actually not 100%. But there is no statistical significance, but QC still improved the participant search accuracy from 83% to 95%, which is still a good improvement. So now we've proved the effectiveness of QC. Now what's the next? So the system still actually have some limitations, which can review potential research directions in both HCI and artificial intelligence. So for example, our current system were trained based on a data set with only 200 products. But in the real world, of course, in the real store, there will be much more products than the 200 products. And also it will be different between all the different stores, which means the data set maintenance and updating can be a very big challenge in terms of the system design. So in the future, I want to collaborate with AI researchers to look into few-shot learning, which can still train reliable model, but based on a much fewer number of data, which can potentially reduce the workload of maintaining the data set. QC is the first intelligent MR system that automatically perceives the surrounding environment and provides direct visual augmentations for people with low vision. Different from the conventional vision enhancements, for example, magnification, that is arbitrarily applied to people's full field of view. My research demonstrated the importance of generating direct visual augmentations by considering the user's context, including both their different visual abilities and their different visual tasks. However, visual search is, of course, not the only challenge that low vision people face. And during my PhD, I've always been looking for the different challenges that low vision people encountered. For example, before you actually buy stuff in the store, you will first need to get to the store. And this process will involve a lot of different navigation tasks. And stair navigation is one of the most dangerous mobility tasks that low vision people face. And prior studies have shown that low vision people have experienced a much higher rate of injuries and falls as opposed to people who are sighted when walking on the stairs. But then how do low vision people navigate on the stairs, and what makes the stairs so difficult for them? To answer these questions, still, I started my research with an exploratory study by observing 14 low vision participants. And surprisingly, I find that the white cane that is typically used by a blind person is not that often used by a low vision person. And during my study, only 4 out of 14 low vision participants used the white cane. And instead, they actively collect the visual information from the surrounding environment during the stair navigation. And one of the most helpful information is the contrast straps, which are these high contrast colors at the stair edges. However, not all the contrast straps are accessible. Many straps, they do not have a contrast that is high enough for a low vision person. And many stairs, they even don't have any contrast straps, which bring a lot of difficulties to people with low vision. Then based on that, what technologies should we build to address this problem for people with low vision? Since the contrast straps are all the useful information that low vision people are looking for, then what if we can generate some personalized and mobile version of contrast straps, so to make the originally inaccessible stairs more accessible? So with that idea in mind, I designed Stairlight based on a projector-based device. So if a user holds a projector-based device like holding a flashlight, and then the system has a depth camera to automatically recognize the stair edges, and then project back different visual highlights to increase the stair visibility. But the problem is, what visual highlights should we generate? Should we simply replicate these contrast straps and generate the same color on each of the stairs? Does each stair mean the same to the low vision person? So to answer these questions, in my exploratory study, I also asked my low vision participants how do they perceive each stair and how do they perceive the different contrast straps. And I find that, of course, not all the stairs, but only the first and last stairs are the most important but challenging for people to locate. And also not all the contrast straps are helpful. If people see all the same color on each of the stairs, it probably messed up with their depth perception. And the participants only want to use the contrast straps to emphasize the first, the beginning, and the end of the stairs. So based on the user's needs, I designed different visual highlight patterns to enable the low vision people to better navigate on the stairs. And specifically for the stair navigation, I first emphasized the first and last stairs, And also I want to minimize the distraction on the middle of the stairs. And following these two rules, I first use the thickness to distinguish the first and last stairs from the rest of the stairs, so that the yellow thick highlights can pop up more to emphasize the first and last stairs. And based on that, I also designed different animation patterns to further emphasize the first and last stairs, so that a low vision person can even notice the existence of the stairs and its exact position even at a far distance to prepare their step. And at the same time, I also provide different color options, including both the dull yellow color and dark blue color, to minimize the distraction on the middle stairs. So based on all these visual highlights design, the user can still select and combine their preferred visual highlights patterns when they use their light on the stairs. So now I want to show the video demonstrating how they use the system. So it simulates the interaction of a flashlight, and the user can point the device to the stairs, and it can recognize the closest 3 or 4 steps of stairs and project the highlights back. And the system can also update the highlights based on the user's position, leading the user to the front. So this is the system design. Still, before we do the full implementation, we first want to evaluate whether the design makes sense. But what should we evaluate? So typically when we evaluate the system, we first think about the accuracy and the speed. But the problem is, for this stair navigation task, do we really care about whether the user can run on the stairs? Probably not, right? For the stairs that can cause so much injuries and falls, the most important thing is whether we can enable the user to navigate on the stairs safely. But the problem is, safety is a very tricky factor to evaluate, because we probably cannot risk the participants by measuring how many times they fall off the stairs, right? It's impossible. And how should we do this? So as a first step, I evaluate the psychological security instead to evaluate the user's actual safety. And this term comes from psychology, which means how much a person perceives her environment to be safe or out of threat. But of course, these two terms, they are not the same, especially when the system can have potential limitations. For example, a person can feel herself to be very safe when she sees some video highlights. But if the highlights are on the wrong position, and then it could be much more dangerous for her. So to address this problem, to reduce the system limitations and make the term psychological security closer to safety, I conduct the study firstly in a more ideal situation, where I set 2 stationary projectors on the top and the bottom of a flight of stairs. And I also use the method called Wizard of Oz, which is a very typical method in terms of HCI, which means a researcher acts as a computer and manually adjusted the interaction. And during the study, I also asked the participants to hold a smartphone in their hand to simulate the experience of holding a handheld device. And with this setup, I recruited 5 low vision participants and asked them to conduct the stair navigation task in 2 conditions. First is their typical walking method. For example, they can use their white cane or hold on to the railings, and as opposed to using the stair light. And based on this study, I asked the participants to give a 7-point Likert scale scores to evaluate their psychological security, to evaluate how safe they feel when they walk on the stairs in these 2 conditions. And I find that stair light significantly increased the participants' psychological security. So based on that, I started to build the system. And this is the sort of works in progress. I first combined Kinect V2 with the Pico projector. And I also attach an IMU to track the user's hand rotation. And I also collaborated with the industrial designer to build a case so that a low vision person can hold all the devices at the same time, like holding a flashlight. And with this device setup, I first calibrate the Kinect with the projector by using Microsoft Room 11 SDK. And also based on the depth map from the Kinect, I conduct the edge detection, line extraction, and also match the lines with the stair patterns to recognize all the stair edges, and then project back all the visual highlights to the stairs. And at the same time, I also use the MU to track the user's hand rotation to correct the user's hand movement during this whole process. Well, based on this implementation, the system achieves the frame rate of about 20 frames per second, which is pretty good if we think about it's rendered on a, say, head-mounted display and everything is digital. However, the problem is now it's a projection system where the physical environment is changing very frequently, so that the user, when they're holding the system, they still can feel the delay. And to address this problem, as a next step, I want to add a position tracking component. And to do that, I want to collaborate with robotics researchers to look into indoor localization. And I also want to try out the state-of-the-art motion capture system. For example, this is a perception neuron, which is a full body tracking system, which can potentially provide the absolute position data when the user are walking in the environment. So based on these technologies, I want to see whether I can use this position tracking component to speed the system up and compensate for the system delay. So I've talked about two examples about how I design and build intelligent mixed reality systems to address the real-world challenges for people with low vision. But at the same time, MR also introduced a new virtual world that can bring a lot of accessibility issues for people with low vision. Researchers have put some thoughts into how to make the VR accessible for people with vision impairments. For example, there have been acoustic VR where people can generate spatial audio to enable a blind person to listen to the different VR environment. And there have been haptic VR where, for example, people can use robot arms to generate haptic or tactile feedback so that a blind person can touch or feel different VR environments. However, the problem is still these systems, they only focus on people who are blind. And also the most important problem is they're all specialized VR, which means they provide accessibility features that are specialized for only one VR application or VR platform. But the mainstream VR, which has lower cost and a higher availability, is still not accessible, which means a low vision person, they still cannot play the same VR game with their sighted friends, or they cannot join the same VR classroom with the other sighted students. So to promote equity and give people equal access to the virtual world, it is very important to make the mainstream VR accessible instead of generating any specialized VR applications. However, we came to the problem that the virtual world is just as complex as the real world. For example, this is one very simple VR application, escape room VR application I downloaded from online, which only have one scene. Let's see what we need to do in this scene, right? So you first need to navigate this room, read the low contrast text, and also find different virtual objects, flip them over, find the different clues, and then get out of this room. So only one simple scene can have so many different VR tasks. And also let me remind you that there are many different low vision conditions that we need to consider. So with all of these different tasks and low vision conditions, how can we answer to all these different situations and create a technology to make the mainstream VR accessible to all different low vision people? So to address this, with my understanding of low vision and also my experience of creating technology to augment the real world for people with low vision, I adapted all the different low vision tools and technology from the real world to the virtual world and designed Seeing VR, which include 14 different low vision tools to cover different VR tasks and different low vision conditions to make the mainstream VR applications accessible. For example, some tools were designed to cover different low vision conditions. For example, this one is called peripheral remapping. It's designed for people with peripheral vision loss. So it generates a minimized and also contoured version of the wider field of view, so that a person with peripheral vision loss can still have understanding of the wider field of view. And also some tools were designed to cover different VR tasks. For example, using the controller to pick up different virtual elements is a very representative task in VR. However, it can be very difficult to a low vision person because many of them, they lose their depth perception. So when they're using the controller to touch the virtual objects, they also always hesitate a lot because they do not understand the distance between the controller and the virtual element. So to address this, I designed a depth measurement tool by attaching a thick laser to the controller, and the ball appears at the intersection point where the laser hits virtual objects, so that the user can observe the length of the laser between the ball and the controller to understand the depth information. And you may notice that most of these tools, they actually do not need any semantic understanding of the scene, which means they can mostly be directly applied to any VR scenes, any mainstream VR applications. So based on that, I incorporate most of these tools into a plugin. And if a low vision user run this plugin on their computer, it can simply modify any VR applications on the computer. And now I want to show a video demonstrating how these different plugins, how my different tools augment the different popular VR applications. So this is magnification for Words of the Wizard, and edge enhancement, very helpful for dark scene.
Solo.
Speech.
Party.
Peripheral remapping. And depth measurement, which is surprisingly very popular for the target shooting game. So this is how the plugin works, and it's very effective and easy to use. But the problem is the information it can augment is still very limited because it does not have any semantic understanding on the scene. For example, what objects exactly are in the scene and which objects are more important that people should focus on. So what if we can get some semantic understanding from the scene and generate more augmentation tools to make the scenes more accessible for people with low vision? So developers are the one who create these applications, and they are probably the one who knows the application the most. So if they can provide some useful semantic information, and based on that, I can generate more augmentation tools to enhance the scene further. So for example, if a developer can provide descriptions to all the different virtual elements in the scene, and then I can design this object description tool to read this scene a lot if the user point to these different virtual objects.
Book. Pillow. Candle.
But the problem is, how should we enable the developers to provide this information? Especially, to be honest, accessibility is really not a top priority in most of the tech companies. So to address that, I built a developer toolkit to enable the developers to provide all the meta input and also integrate all the low vision support during the development process. And the current developer toolkit focuses on Unity, which is one of the most widely used VR development platform. So this is the very typical Unity editor user interface. And the developer can simply add different game objects into the scene, for example, a cube. And then they can use this inspector tab to adjust the different features of the game object, including their position, a rotation angle, or scale, and so on. And to enable developers to provide more information for our tools, my toolkit first modified the Unity editor by adding 3 accessibility features to the inspector tab. For example, this is the description feature. so that the developer can simply tap in the description of any game object, for example, a pillow on a table, and then later this object description tool can easily read this information a lot if the user uses it. So I've talked about the low vision tools and also the developer toolkit, which means there are two groups of users for my technology. One is the end users, the low vision users who's going to use the low vision tools, and we want to make sure these tools can effectively improve their VR experience. And also the Unity developers who's going to decide whether they want to use the toolkit. And we want to make sure they feel the toolkit is easy and effective to use. So to answer these questions, I conducted 2 separate studies. And I started with the 11 low vision participants, asking them to conduct 3 representative VR tasks, including menu navigation, visual search, and target shooting. Also in 2 conditions, their best correction, and also seeing VR with their preferred tools. And I find that seeing VR significantly reduced the participants' time across all the different tasks, and also improved all participants' VR experience. Actually, besides our participants, seeing VR has already shown its impact on the broader audience. So several days ago, I encountered this YouTube video, which was uploaded by a low vision person called Illegally Sighted, and he made comments on all the different seeing VR tools, and here is part of his comment.
Honestly, this toolkit and all of the things that they've already implemented solves the vast majority of all my complaints and concerns and frustrations that I've had trying to use virtual reality interfaces. You know, the text and interface items being a set distance from your face, and you can't get closer because it keeps moving away. Things being far away, things blending in. Contrast, just any number of things. I mean, this addresses so many issues. I love, again, the idea of the magnifier, the high contrast, the text-to-speech, some of the outlines and colors things. This is kind of the breakthrough that I've been hoping for, that I've been dreaming about.
So the reason I play this video is I want to emphasize. So this person, he has low vision, and he actually uses a lot of mainstream VR applications. And he also talked a lot about his difficulties when using these mainstream VR applications. So it emphasizes the importance of making the mainstream VR accessible instead of generating any specialized VR applications for people with low vision. And in terms of the developers, I also recruited 6 Unity developers to use the developer toolkit. And all the participants find the toolkit is easy and effective to use. And the interesting thing is some developers also emphasize the importance of the toolkit towards the general MR accessibility framework. As one developer mentioned, we sometimes got asked by the accessibility team at our company, you need to be accessible, but they don't really understand what accessibility is in the VR context. You're the first that actually look this deeply into this problem. And to make a bigger impact, my Seeing VR toolkit is now open source on GitHub with all the different low vision tools. And now developers can simply download them and make more accessible VR applications. So Seeing VR is only the first step towards the general MR accessibility framework. And it actually has posed a lot of questions and challenges towards this big direction. So for example, currently Seeing VR focuses on people with low vision, but there are many other disabilities that people need different accessibility support. And also mixed reality is not only about the virtual world, it also includes the physical world. And then how can we accessibly convey the information from both the virtual and the physical worlds? And how can we convey the relationship between the virtual and the physical worlds? These are all challenging questions that I want to answer. And at the same time, we want to provide people equal access to the 3D virtual and physical content, but we also want to provide people equal access to the immersive experience that MR are supposed to provide. And then how can we create a technology that provides people both equal access to the content and also the good immersive experience of MR? And also how much human effort should we put there? So my research, I built a developer toolkit, but does that mean that it's all the developer's responsibility to make VR accessible? Probably not, right? And then maybe should we make this whole process automatic? For example, can we use any AI technology to recognize different VR scenes? How would the different AI models work in the VR scene, and should we construct a new VR data set to address this problem? And also in between, can we use crowdsourcing technology to enable other mixed reality users to provide some useful information? And then we can use this to create better tools to augment the scene for people with disabilities. So these are all interesting and important questions to answer towards the general MR accessibility framework. And in the future, I want to collaborate with researchers in AI, graphics, crowdsourcing, and also not only researchers, but also developers, designers, even policymakers to together address these big problems. So at the same time, I also see the great potential of MR for accessibility in empowering people with diverse abilities. So my PhD research mainly focuses on people with low vision and more individual functional tasks. For example, reading, navigation, shopping, and so on. But in the future, I'm also very interested in more complex tasks that involve multiple users. For example, social interaction and work collaboration, which can also involve different privacy, social acceptance, and also ethical issues. And I want to explore what roles MR technology could play in this more complex multi-user scenarios. And also, I want to extend my target users to other cognitive and perceptual disabilities. For example, people with autism, people with learning disabilities. And during my PhD, I've advised master's students to explore how to enable children with autism to better perceive other people's facial expression via 3D emojis. Well, this work is very preliminary, but I also see it as a very good start when I want to extend my target users. So I believe in the future of mixed reality, and I believe in that in the next 20 years, maybe everyone will wear smart glasses and the projectors will be embedded into all the physical environment so that all the physical interfaces, physical surfaces would be interactive. And with that vision in mind, I believe that it is very important to think about how to make the best use of this technology, how to best leverage and also shape this technology to make it better serve and empower people and promote equity for everyone. And today my talk, I focus on 3 of my research projects, QC, Steerlight, and Seeing VR. But I've also worked on many other research projects towards accessibility, augmented reality, and artificial intelligence, which were all released on my homepage. And if you're interested in, please feel free to take a look. And I'd also love to talk about them offline. Thank you so much.